is about integration of online trace aggregation, online aggregation tools with trace buffering approaches, and what can we do by combining both. So I am the CEO at EfficiOS, maintainer of LTNG, part of the Linux kernel, the member system called user space RCU and file trace. So we're going to start by comparing trace buffering approaches and in-place aggregation, because there seems to be overall some confusion between the two approaches. We're going to show how we can automate problem analysis by combining both approaches. Then we'll move on to some demo, benchmark, and future work. So the rough idea of trace buffering, as is done by LTNG, ftrace, perf. So you basically store events into a ring buffer, and you perform the analysis at post-processing. So you read back that buffer and perform whatever analysis you're interested in. So one advantage of the trace buffering approach is that on that same recorded trace, you can run analysis for hours and hours and look at the problem for various angles with the data you have recorded. So compared to that, if we look at in-place aggregation, this is the case of eBPF that appeared recently, dtrace, system tap. They will basically run the analysis directly on the event input within the execution context that generates those events. So they directly perform aggregation in the trace execution context. So what the nice thing about in-place aggregation is that you can respond to those events very quickly. So whatever generates a very high abnormal threshold, for instance, you can immediately respond. Whether for trace buffering, then you have a delay caused by the buffer. So they are very often presented as competing solutions. However, what I'm presenting here is that they can actually be combined to create much more powerful tools than each of them individually. So here what I'm showing is a diagram of how we can integrate those tools together. So in this example, I'm going to present the latency tracker done by Julien at EfficiOS. So the main goal of this latency tracker is to track long response time. Then that latency tracker can wake up a trigger script, which can then ask LTTNG to gather a snapshot. So as we run our workload, we have the latency tracker looking for abnormal situations, and we have LTTNG keeping a flight recorder trace of data in memory buffers. So it's not doing any I/O. But when we detect a long latency, then we ask to gather LTTNG to grab a snapshot and send it over the network or to disk. Then, that allows doing post-processing analysis on that data and understand from various angles what's happening in the system when the long latency was detected. So then I'll present trace compass down trace that are with which you can dig further into the information. So first, the latency tracker. So it's a kernel module that tracks down latency problems at runtime. So it's not in the mainline kernel. It's on the out of tree module, but there's no kernel modification required. It provides a simple API that can be called from tracepoint, kprobe, the netfilter hook. That could even be called just as in and out event. I'm going to show this API in the coming slides. And what it does basically is to keep track of entry and exit events. And then, so let's say you have an IRQ entry, IRQ exit for an IRQ ender. And then if the delay between the entry and exit go over a specified threshold, then it's going to call a callback. So the API is as simple as this. So you have the event in, event out with a key. So, and we use that key to match the in and out events. And then the threshold, so it's specified when you create the tracker. And then, so we also have a timeout and timeout parameter. So if there's been an in event but no out event, after a specified timeout, then we are going to basically remove the entry and call the callback. So the design of the latency tracker aimed at mainly being low impact, low overhead. So we created our own custom memory allocator using a log-free per CPU or CPU-free list with pre-allocated new modules. It's an out-of-context worker thread that expands the memory as needed up to a user-configurable upper bound. Before 3.17, we needed to implement our own color CU thread to avoid wake-up deadlocks due to the way wake-up was working. For color RCU scan, sorry. And then from 3.17, then we can use a color CU scan to do that. It works. We can call it from various contexts, and there's no problem there. So that's to allocate memory. Then to do the actual state tracking of what's happening in the system. Basically, we have those event in, event out, so we put that in a hash table. So that hash table is the user space RCU log-free hash table that we ported from user space to the external. So it supports log-free insertion and removal as well as wait-free lookups. So all this can be used even from an NMI context. So that was one of our goals. So the latency trackers that are currently implemented, so we have one tracking what's happening at the block layer, from block request issue to completion. The network layer, wake up, so from wake up to waking event to next scheduling of a thread. Off CPU time, so preemption blocking to next execution. IRQ handler entry to exit, system calls are tracked. And a new one appeared recently, time to first byte. So it's between the accept system call return and the following write system call on that same item. So this way, so it's a pretty typical pattern for server processes. So it's a nice way to track those. So an example of the model, how we track state in the hash table. So in this case, we start with we always start with the RQ entry. And then, as we go down through the states, let's say that we reach soft RQ rates. So it's actually forking the states. On one side we exit the RQ, but then on the other we eventually enter the soft RQ entry, which is linked to the soft RQ rates. Then the soft RQ can perform a sched waking event, which is going to fork again in the state, and we reach the sched switch. So this way we can follow from the do RQ entry to the raise, to the sched waking, to the sched switch, and across sched waking, sched switch. We can follow execution chains, so critical path from the start of so whenever the operating system has received an interrupt from the external world, do RQ entry, down to whatever it actually completes the response to that interrupt. So we can track the longest response times with that.
So where does the soft RQ crap come from? We don't do that.
The do RQ entry or the soft RQ? So this is not for
the whole soft RQ stuff doesn't happen.
You're talking about the preempt RT kernel or a mainline?
Mainline.
So this soft RQ raise and soft RQ entry?
Is it preempted or
so
the regular wake ups? We don't use soft RQ.
No, that's right. But from an interrupt handler, there are some the device drivers issue soft RQ raise to raise a soft RQ, and it's then executed afterward. So it's a delayed handling of interrupts. So mainline does that. Preempt RT is all usually threaded.
But this is to give drivers. This is not a regular scheduled path.
No, so we instrument the scheduler, but we also instrument soft RQ and IRQ handling, so we can follow the entire chain.
Okay, but this is not a normal path.
I think he's just showing the example of a complex path.
Yeah, but
the other way is probably a little more trivial.
From the interrupt entry, most of the path, if you look at network path, for instance, they're going to go through a soft IRQ, and then they're going to wake up a thread,
they do a lot more.
Uh,
That's just some of the networking crap.
Depending, yeah. I mean, if we look at the next one, this guy is for preempt but typically it starts with an IRQ, goes to a soft IRQ, and then can chain multiple times through the scheduler with wake up and
Only
schedule.
networking stuff. Most of the other drivers just do the wake up from hard IRQ context.
Yeah, and that works too. Yeah, that's just some more complex case that goes through a soft IRQ. So for a preempt model, it's a bit more convoluted. So the difference is, preempt supports threaded interrupt enders, and then for those threaded interrupt enders, it's actually the interrupt context is going to execute the IRQ enders if there are some, and then it's going to wake up the IRQ pending thread. So this happened after the ender execution and before the do IRQ exit. Then we basically monitor the sked switching, which can then wake other threads, or raise a soft IRQ, which can then wake up other threads. So this is really the model for the online critical path analysis. So it measures response time. It performs tracking of execution, context, wake up chain as a kernel module. Works on mainline, RT kernel. Currently supports instrument IRQ, soft IRQ, wake up scheduling chains. Currently it does not work on NMI, but it could. It follows critical path from interrupt servicing to completion of the task. And we also, and basically it can wake up a user script to perform user-specified operation whenever a long latency that's higher than a specified threshold is detected. So parameters that can be passed to the latency tracker module. So latency thresholds, we can have filters on those chains. So we can say that we're only interested in specific IRQ or soft IRQ numbers, so only consider when those are within the chains. Whether we're passing through a real-time task as we go down the chain, so those will be the only matches. By process name, PID, and whether, so if a chain only stays in the kernel, in kernel threads, and does not reach user space at all, we can remove all those chains also. We can specify whether we want those chains to stop when a user task starts to run or when it's blocking. And we now support tracking work begin and end from user space. So we expose I think it's a proc file, to which user space can write an identifier, a key, to say, okay, I'm beginning some work, and then I've completed my work. So what we can do with it, the latency tracker can track from the IRQ arrival down to user space, work begin, and then that work can be done through multiple processes collaborating with each other, and it's only completed when we see that same key as a work end matching. So basically we can track across various processes, even in cases where those processes actually have synchronization point that would be user space only and would not involve a wake up. So, okay, so that's for online tracking. Now I'm going to kernel and user space tracers. Going quickly on this because this is things that have been that has existed for a while now. So the LTTNG kernel and user space tracer. So it provides correlated tracing of kernel and user space. With the ring buffers and shared memory, supports user-defined filtering on event arguments. System-wide tracing the whole system or tracking specific processes. And it can optionally gather performance counters from a perf into alongside with the events, an extra field that has context. So it supports this IO output, in-memory flight recorder, network streaming, live report. So the LTTNG kernel tracer, LTTNG modules, again, I've been telling that for about 6-7 years now. So LTTNG does not need any kernel patching anymore. So it's a set of out of tree kernel module which can just be loaded into a vanilla kernel or a distribution kernel. So you don't need to modify your kernel to use it. And it uses trace points, system call entry exit, instrumentation. But one strength of the LTTNG module is that it does a large part of what strace does, but much more efficiently. So we extract a detailed argument of most system calls, which is not done by the other tracers like trace. We work on kprobe, kretprobes. For the user space counterpart, so LTKNG UST, it's a dynamically loaded shared library. It does fast user space tracing. The fast path is entirely in user space, even for reading time, for getting the current CPU number, and that's all shared memory. So we can instrument application and libraries with the LTKNG UST trace points. We also have kind of printf-like statement that can be added to application for a quick debug style tracing with traceset and tracelog. We provide adapters for Java, JUL, and Log4j loggers, Python loggers, and we can trace malloc, pthread mutex operations with a LD preload helper library. And we can trace function entry exit. Currently it's by fh functions, so it's slightly more overhead, but that can give very useful information. Recently, this year, we've added dumps of library-based addresses. So we can basically map the events that are traced to their source file and line number if you have the dwarf information. Or we can also map to the functions and offset and function that contains them. If you have dwarf or elf, so whichever you have, we provide as much information as we can. So for another project, LTKNG analysis. So going back to this. So I talked about the latency tracker, which will track long latency online, trigger a script. I talked about LTKNG, which records events into a flight recorder, always overwriting the oldest information. And then once the snapshot is taken, so it really identifies an area so events that were of interest that led to the problematic scenario, then we can use LTKNG analysis on this snapshot. So those are offline analysis based on LTKNG traces. So we allow analyzing CPU usage, memory usage, input-output operations, both at the file descriptor and at the block I/O level, interrupt activity, scheduling, system calls. So it provides distribution, top, log, everything over a threshold of all those things. So the ones I did not list is so thread wake-up latency from sched waiting to sched switching, and the nice addition, recent addition, is the ability to have user-defined periods based on kernel and user space events. So basically, you can define whatever periods you want in a nested fashion, and it's going to give you aggregated statistics on those periods. So I could do a whole talk just on that, but have a look. It's fun stuff. By the way, we'll very soon put on YouTube the talks we presented at LinuxCon in Toronto, and there's a presentation from Jérémy Calarno on that topic.
It's present.
It's there already. Good. Thank you. And we did an integration of LTKNG analysis with the Trace Compass graphical user interface. I'll have a small, I have a few slides on this. This is a proof of concept that Julien Desfossé did a few weeks ago. You can actually go on that website if you like. This is a temporary website for to show it. Actually, I'm going to demo it live. Yeah, that's it. So this is using Grafana. We just configured Grafana to take as information input what's being collected by the latency tracker. So it's the latency tracker running on a server system. And then we specify a threshold around 100 milliseconds. And this is the time to first byte. So between accept and the first write reply on that same file descriptor, the same title. And then having specified everything that has a response time of more than 100 milliseconds is an event of interest. So what we do, so it's been configured to gather a snapshot, a LTKNG snapshot, whenever that happens. And then, as you see, if I move my cursor over that point, I can ask for a report. And this is the output of LTKNG analysis, which has been run on that snapshot at this point in time. So we have information. So go to our graph. So per thread ID, CPU usage. Hopefully you guys see well. Yeah, I'll graph this way. Yeah, I don't want to make it too large because yeah. So here we have per CPU usage information. We do have system call latencies for open, read, write. And this is basically at the top, so the longest duration. And then we have the timestamp in the trace where that happened. And you actually have that trace sitting around, so you can look deeper and see what was happening surrounding that area. So we have per process, input, output, read, write, and sync information on a per process basis with statistics. We have that on a per file basis also. Network, received byte, sent byte. We have the system calls, overall statistics. We have, so this is memory allocation on a per thread ID basis. So at the page granularity, remember this is using kernel tracing information. And we have a scheduling top. So these are the longest wake up to scheduling latencies. And then we have the timestamp, so you can actually use things like trace compass and go look at what was happening, what was sitting on the system, because they're causing those latencies. And then we have that per thread ID also as a breakdown. So when we have the min, max, average latency for each. Okay, so so this, oh, actually one more thing. So this was the time to first byte.
So, but it's showing Chrome talking to Apache locally or some application, or basically what was the actual test?
I think it was Apache, but I could not say for sure. It's Julien's deployed it on a machine that does a few things, so I could not say exactly which one it was. But then, I mean, in this one we took the time to first byte, so it's between accept and write back. But I mean, if you have so a single connection that stays open for a long time, it does not really fit in that pattern. So you might want to put extra instrumentation in user space and put things on that. And then there's the response time analysis. So this is the output of the latency tracker, which is kind of processed. So this is RRQ to blocking state, so the period minimum, average, and maximum. So delay between really the do RRQ entry to wherever that chain starts to block. We have the complete response time on a per host basis, RRQ to scheduling latency, and we have the breakdown by priority, breakdown by RRQ number. So again, I mean, if a chain reaches a specific process priority, thread priority, that's interesting to us. For breakdown per RRQ number, number of RRQs observed that woke up, ended up waking a target process by process name. Same thing, max processing time by process, as well as latency breakdown. So there are a lot of very interesting metrics about response time that we can extract from the latency tracker. Then we can drill down much further with offline analysis, with EfficiOS analysis. So this is a nice way to kind of present that information so it's easier to consume. So next aspect is Trace Compass. So it's a graphical user interface which is useful for correlating trace analysis results with detailed graphic representation. So once you are at the point where you know, so if you identify your problem, you know when in time approximately it happened, and you have statistical tools to figure that out, then we provide graphical analysis tools to dig even further. So Trace Compass has its own analysis, but we also created a JSON interface, which we call the spec is called Layline. So it's an interface to extract data from the external analysis scripts back into Trace Compass. So this is an example of Trace Compass, where we have the control flow view. So it's a the state per thread through time. So we can see in green it's running in user space, in blue it's running in a system call. So we have the various state that we can follow. We have something similar on a per resource basis. So every CPU, all interrupt lines, a sub-tire queue, we can follow what is happening. Then this is an example of so integration of LTK-NG analysis with trace compass. So this is a breakdown of interrupt handlers duration. This is a frequency distribution. So basically what we're doing, so on a given trace segment, we're asking to compute what's the duration of the interrupt handlers from entry to exit. And then we ask for a breakdown of counts. So how many we have of each. And this is a multi-series distribution with a breakdown by interrupt handler. So in this case, so in blue, it's I-8442, I think it's probably my network or mouse. We have interrupt 12, again, that's probably the mouse. We have network and Wi-Fi. So we can see that from this breakdown quite quickly. So at the right, we have the top ones. And this is, so we can put it in log scale. It's actually useful in this case because not log scale, we wouldn't see anything at the right. And then we can find the outliers. So that's one. Another one is the same thing. It's a multi-series distribution, but this is for scheduling latencies frequency. So we can see here, so it's group by priority, and you can see, so at the far right, you actually have 6.5 milliseconds, and this is for priority 20. So, but you can see that everything seems to be grouped here. And again, I had to use the log scale to see the information that's at the far right. So, now, yeah, just go ahead in a few minutes. Actually, maybe. So just, maybe, let's go back to that later. So bubble trace, that's the other part of that picture. Again, if I go back, we're almost done. We can view traces as text logs, so when we want to dig deeper. So bubble trace, it's a common trace format trace reader and converter. Performs time-based correlation and merge. So basically you can take trace sources from the kernel, from user space, and it's going to show that within a single timeline. It exposes C, C++, Python APIs to read CTF traces, and currently it allows printing traces into desktop. So I have some demos. I have to go quickly. So the first one, it's a periodic use case. So it's the Jack audio server on which we have scheduling latency caused by unsuitable priorities, so misconfiguration. So let's have a look. Jack. So it's a video. So we basically start by loading the latency tracker and the latency tracker RT kernel modules. Then we start the Jack audio server, specifying that we want it to run on CPU 0, priority 1. So it has started. So basically we have, I think I missed it, but we have, I think it's 21 hertz or something like 21.3 millisecond is the period that is expected. So what we'll do, we'll set up the latency tracker, I think it's to 25 milliseconds, so to give a small buffer and as a threshold. So whatever hits that threshold is going to be enabled. So, and we also set up a flight recorder tracing with LTK-NG. And this is how we can configure the latency tracker. So we start that script, and what it's going to do is to wake us up so we can take a snapshot whenever the threshold is reached. So here, what we've done, we've run CPU burn on that same CPU with a higher priority. So we are really creating a problematic scenario. We can see at the left side that Jack has detected that scenario. It has internal detection of buffer overrun and underrun. And we can see at the right side that we have triggered a snapshot. So we'll run ScanTop on that snapshot. So it's 530, it's not so fast, but there's room for improvement. Here what we see is the top scheduling latency, and we can see Jack happens to be at the top. And we have the time range corresponding to that very long scheduling latency. So we'll take that time range and run LTKG CPU top on that same trace on the time range. So that should give us the culprit. So indeed, we ended up seeing that CPU burn took nearly 100% CPU on CPU 0 during that time duration. All right, so that was the first demo. The second one. So, I mean, okay, if you can monitor, if you have a periodic workload on your application, you can detect those problematic scenarios from the application. But what happens if your workload is non-periodic? It's kind of harder to track those long response time delays. So we took memcached, which is a distributed in-memory object caching system, and basically we looked at the response time to both start ending client query and complete ending. So let's go back to the email. All right. So basically we're starting the latency tracker. And okay, so this is just to show that if we can, so we act as a client to the memcached server which is started on that machine. The client is on a different machine. We can see that the latency tracker is showing us that some latency has been detected, but this was with a very, very low threshold. So we have some activity on the system. That's great. So now what we'll do is change the threshold a bit higher. We can see that, well, okay, we connect with the client, but we don't see anything anymore. So we'll stop memcached, and then what we'll do, so now we have the latency tracker set up at a level at which, with normal traffic, it's not triggering anything. But then what we did here is to start memcached just with verbose log going to the file system. And whoops, we now see again that we have long response time. So what it shows us is that enabling verbose log, just a misconfiguration. I mean, a sysadmin might enable those logs into their system, and they happen to leave them there, just forgot about them, and then you have a longer response time. So these are the kind of things you can track with the latency tracker. So some benchmarks. So memcached on a gigabit interface, so with the 10,000 requests, the baseline is 491 millisecond response time. With the tracker, it becomes 520, so for roughly 6% overhead. So the further benchmarks in terms of CPU memory, so the overhead stays roughly under 6% on the various scenarios when you add the tracker. We have more detailed benchmarks in terms of, so we use perf to basically look at it, L1, LLC, TLD misses, and they stay pretty low. So so this is when you have transitions of state, and we have no transitions, so the two have different performance impact. And we typically have, from the DoIRQ down to going to the user space process, we typically have about 8 transitions, so it gives a rough estimate of latency around 8 microseconds to a request. Some future work, exposing the API of the log-free memory allocator and hash table that we use in the latency tracker to eBPF scripts. Eventually that might be interesting. So it provides interesting NMI-safe and log-free type of execution, which might be nice to integrate within the kernel. So it would allow hooking eBPF scripts to perf that are triggered whenever a performance counter overflows, and then using those data structures. And one thing we could do, so currently the latency tracker is implemented in C, but we could re-implement that as eBPF high-level code eventually. So here are the links to the various projects. So LTTNG, the latency tracker, the LTTNG analysis scripts, trace compass, bubble trace, and the common trace format. Any questions?
The ring buffer implementation in USP.
Yes, microphone.
Actually, the ring buffer, when you use LTTNG USP, is that memory map?
Yes.
So everything is, so that memory is managed by the kernel and then
No.
mapped.
So the memory is allocated by the consumer daemon, which is a user space process, and it's passed to the application over Unix sockets. So it's a file descriptor being passed over a Unix socket, and then it's mapped again in the application.
Okay.
At the back, yes?
Are you going to publish the slides somewhere?
Yes, the slides are going to be published. So the exact URL for the for this because this URL is currently online, and we plan to perhaps keep it online for 1 week or two, but we might move it to a more permanent location for demo. I mean that's a short yeah, that's a proof of concept that we have released.
Actually, that's exactly what we're looking for. Just one thing I'd like to understand between interrupts and worker threads or whatever, there's a kind of end-to-end relation. I mean, we can have a time interrupt which is triggering, I don't know, 5 or 10
Yes.
threads.
Yeah.
And we can, on the other end, have maybe a driver which is triggered by various interrupts. So how can you specify that in the configuration of selecting these things if you want to specify a number of interrupts and maybe a number of threads which belong to that scenario?
So currently the filtering machinery we have in the latency tracker specifically, we currently only can specify either all interrupts or one interrupt. We could extend that to specify a few, and this is by interrupt line number. We also allow, and those are kind of addition filters, so it's one needs to match one and the other. So if you filter by interrupt line, then we can filter out things very, very quickly at the beginning of the chain tracking, so it's more efficient. But then, I mean, if you want to also scope with a specific user space processes, for instance, then, I mean, this gets filtered out at much later in the chain, pretty much at the end of the chain, because we can go through various wake-up chains and go through various processes. So, and as soon as we reach the process that you have specified as a filter within the chain, we want to keep that chain. So this is currently what we allow. So, but in the case where, let's say you have an interrupt line that has multiple interrupt enders and wake up various things, if you filter saying that you're interested in this interrupt line, we'll follow all the chains that end up being taken by all the various drivers which are connected to that interrupt.
One more. If you have one kernel worker doing maybe, let's say a UART driver gets the interrupt and then the kernel worker takes the load, that there might be another kernel worker which may be used for putting the data into a PPP socket. So the question is the first worker, is that the end point of this latency, or can I maybe have multiple workers which trigger each other for the complete latency chain?
So if you put, let's say that you queue stuff, and we've seen that a little bit with QoS, for instance. And I mean, there might be some tweaks to do eventually for this kind of thing, but so if you have throttling of network traffic with QoS, then basically you put things in a wait queue, and my understanding is that it gets eventually done when the timer fires a bit later. So it's not the network interface packet arrival that's the source in this case. It becomes the timer firing that's the source. So you have to be aware of what you're using. Yeah. So and whenever things are put on a wait queue, this kind of breaks this may break the chain if whatever is basically restarting that processing is, for instance, a timer.
So basically, you need to have a scan wake up for keeping the chain, right?
Yes, exactly.
So if it's not directly connected, then the chain is broken somewhere.
Exactly. Other questions? If not, we'll take the break. So let's see when we come back.
We have to be back here at 11.